Так, всем привет, я тут макароны кушаю просто, да. Собственно говоря, приступаем снова к разработке ОС. Собственно, как вы помните, у меня уже был первый опыт. Применял я его на практике, так сказать. Давайте покажу. Вот такой вот первый опыт. Собственно, вот так вот эта штука могла выводиться. Сегодня мы будем смотреть курс от нанобайта Building NOS. Я посмотрел, тут очень много материала, также много людей писало то, что это вообще просто самый лучший, просто нафиг, просто самый лучший курс, на нем все рассказано, все написано, и плюс это хорошая заготовка для ОС. И я буду, получается, у меня 7 вечера, да. По будням я, конечно, не в такое время снимаю, но собственно, я и снимаю только в будни. Давайте сразу удалим все, что здесь существует. И все, вообще все на свете, так все. Включим перевод, субтитры, перевести русский, и погнали.
Hello and welcome. In this tutorial, I'll show you what it takes to build an operating system from scratch. So let's jump straight into it. First, let's see what tools we will need. For editing text, any text editor will do. I will use the micro editor, which I really like because it uses common keyboard shortcuts, but you can use anything you like. We will use make to build our project. Next one will be our assembler, which we will use to assemble our assembly code. We will also need some virtualization software. I will use Camel, but you can use any virtualization software you like, such as VirtualBox, VMware, or anything else. I will be using Ubuntu in this tutorial. If you want to follow on Windows, your best option would be to use the Windows subsystem for Linux. You can find a tutorial on how to set that up in the video description. The second option would be Cygwin, which has most of the tools that we need. On macOS, you shouldn't have any trouble finding these tools using Homebrew. Let's create a source folder in our project.
Стоп, поменьше шрифт. Окей, достаточно. Так, так и вот так.
Inside, we'll make a file called main.asm.
Понятно.
The first part of our operating system will be written in a programming language called assembly. Later, we will be using C, but right now we don't really have a choice and we really have to use assembly. So what exactly is this assembly thing? Shortly, the assembly language is a human-readable interpretation of machine code. When you compile a program in a programming language such as C or C++, it gets converted into machine code, which is the language that the processor understands. Assembly makes it easier for us humans to read and write machine code. Higher-level programming languages such as C or C++ need to be translated by the compiler into machine code. This involves many steps, like building an abstract syntax tree and a huge amount of optimization. Assembly is much simpler, because the instructions simply need to be converted into their machine code representation by a tool called an assembler. An assembly instruction is made up of a mnemonic, or a keyword, and a number of parameters, which are called operands, typically 0, 1, or 2 operands. An important thing I'd like to mention about the assembly language is that there are differences between different processors. The instructions supported on an x86 processor that you find on laptops and desktops are different than the instructions supported on an ARM CPU, which is found in smartphones or tablets. Even different processors with the same architecture might have differences. For example, SSE is a feature introduced in the Pentium 3 processor line that didn't exist in the Pentium 2 line. However, newer processors usually keep backwards compatibility,
Но честно, не особо понимаю такой перевод корявый.
so that old programs can still run without any modification. Backwards compatibility for the x86 architecture goes so far back that it can still run software on a modern computer that was designed for the 8086 CPU, the first CPU ever made using the x86 architecture, which was released 40 years ago. So, to be clear, we will be writing our operating system for the x86 architecture.
Так, Nautilus как находят, то есть это я знаю, то есть адрес 700 видно 16,
$1 million and a new million gold elixir, Marabas.
Von vielen bekannten Marken, Rede Bio und ja,
Это я
kannst du den
знаю.
Preisvergleich sparen. Discount zahlen, Rewe bekommen. Rewe, dein Markt.
Putting our program on a standard 1.44 megabytes floppy disk, where one sector has 512 bytes. The BIOS requires that the last 2 bytes of the first sector are AA55. We can ask NASM to emit bytes directly by using the db directive, which stands for declare constant byte. The times directive can be used to repeat instructions or data. Here we use it to pad our program so that it fills up to 510 bytes, after which we declare the 2-byte signature. In NASM, the $sign can be used to obtain the assembly position of the beginning of the current line, and the double $sign gives us the position of the beginning of the current section. In our case, $- gives us the length of the program so far measured in bytes. Finally, we declare the signature. DW is a directive similar to DB, but it declares the 2-byte constant, which is generally referred to as a word. With this, we have successfully written our first operating system. So far, it doesn't really do anything but stop the processor. Let's test it if it works. I created a build directory to keep things organized. For building the project, I created a make file. I added a rule to build the main.asm code using NASM and output in a binary format. I added a rule to build the floppy disk image, where I simply took the binary file previously built and padded it with zeros until it had 1.44 megabytes. Finally, we can test our little operating system.
Окей. Нормально.
Finally, we can test our little operating system. You can use any virtualization software you want, such as VirtualBox, VMware. I use Camel because it's really easy to set up and it can be used from a command line. As you can see, the system boots from floppy and then it does nothing, exactly as we expected. So far, our operating system does nothing and does it perfectly. Now that we know it works, let's go back to the code and print a hello world message to the screen. Before I start explaining how you can do that, I need to explain some basic concepts about the x86 architecture. All processors have a number of registers, which are really small pieces of memory that can be written and read very fast and are built into the CPU. Here's a diagram of all the registers on an x86 CPU. There are several types of registers. The general purpose registers can be used for almost any purpose. The index registers are usually used for keeping indices and pointers. They can also be used for other purposes. The program counter is a special register which keeps track of which memory location the current instruction begins. The segment registers are used to keep track of the currently active memory segments, which I will explain in just a moment. There's also a flags register, which contains some special flags which are set by various instructions. There are a few more special purpose registers, but we'll only introduce them when we need them. Now we will talk a bit about RAM memory. The 8086 CPU had a 20-bit address bus. This meant that you could access up to 2 to the power of 20, which means about 1 megabyte of memory. At the time, typical computers had around 64 to 128 kilobytes of memory, so the engineers at Intel thought this limit was huge. For various reasons, they decided to use a segment and offset addressing scheme for memory. In this scheme, you address memory by using two 16-bit values, the segment and the offset. Each segment contains 64 kilobytes of memory, where each byte can be accessed using the offset value. Segments overlap every 16 bytes. This means that you can convert a segment offset address to an absolute address by shifting the segment 4 bits to the left or multiplying it by 16 and then adding the offset. This also means that there are multiple ways of addressing the same location in memory. For example, the absolute address 7C00, which is where the BIOS loads our operating system, can be written as any combination that you can see on the screen. There are some special registers which are used to specify the actively used segments. CS contains the code segment, which is the segment the processor executes code from. The IP, or program counter register, only gives us the offset. The DS and DS registers are data segments. Newer processors introduced additional data segments, FS and GS. SS contains the current stack register.
Spieglein, Spieglein an der Wand, wie bekomme ich das sauberste Lächeln im ganzen Land? Nicht mit deiner Handzahnbürste. Sie lässt bei jedem Putzen 50% Plack zurück. Steige daher jetzt auf eine elektrische Zahnbürste. Die neue Oral-B IO2 wurde extra entwickelt für Einsteiger. Spürbar sauberere Zähne oder Geld zurück.
Найди точку.
Unser Gehirn ist genial. Es kann eine Idee erschaffen und sie groß machen. Größer. Und größer. Und was unser Gehirn nicht kann, können Sie mit einer Website von Strato für nur €1 pro Monat. Strato.
Ну давай, Ира.
In order to access data outside one of these active segments, we need to load that segment into one of these registers. The code segment can only be modified by performing a jump. Now, how do you reference a memory location from assembly? We use this syntax. A segment register followed by a colon followed by an expression which gives the offset put between brackets. The segment register can be omitted, in which case the DS register will be used. The processor is capable of doing some arithmetic for us as long as we use this expression. The base and index operands can be any general-purpose processor registers. In 16-bit mode, there are a few limitations, however. Only BP and BX can be used as base registers, and only SI and DI can be used as index registers. These limitations exist because of how the 8086 CPU was originally designed, where they had to put such limitations to keep the complexity down. Another example of one such limitation is that we can't write constants to the segment register directly. We have to use an intermediary register. With the introduction of the 386 processor just a few years later, 32-bit mode was introduced, which pretty much rendered 16-bit mode obsolete. A lot of newer CPU features were simply not added to the 16-bit mode because it is obsolete and it only exists for backwards compatibility. It is still useful to learn because most of the things that apply to 16-bit mode apply to 32-bit or 62-bit mode, and it is much simpler. Its main use today is in the startup sequence. Most operating systems switch to 32 or 64-bit mode immediately after starting up. We will do the same thing in a future video, but we can't just yet. For now we are limited to the first sector of a floppy disk, that is 512 bytes, which is very little space. Once we are able to load a file from the floppy disk, we can do a lot more. All operating systems have to do the same thing in order to boot. But until we get there, let's get back to referencing our memory locations. So, I already talked about the base and index operands. The scale and displacement operands are numerical constants. The scale can only be used in 32 and 64-bit modes, and it can only have a value of 1, 2, 4, or 8. The displacement can be any assigned integer constant. All the operands in a memory reference expression are optional, so you only have to use whatever you need. So here's an example. First, I define a label which points to a word having the value 100. The first instruction puts the offset of the label into the AX register. The second instruction puts the memory contents where our label points at. Since we didn't specify a segment register, DS is going to be used. We haven't used the base, index, or scale, but only a constant, which is the offset where label points to. In assembly, labels are simply constants which point to a specific offset. Here's a more complicated example where we want...
То есть, как я понял, заварили, давай 155, у нас есть функция start и там обязательно функция start, поэтому у нас есть регистр AX. Вот это получается просто загрузить в регистр, а вот это копировать регистр. Ну, как я понял, будет известно. Правьте в комментариях, кто знает. Смотрит это видео.
to read the third element in an array. In this example, we put the offset of the array into bx and the index of the third element in si. Since we use zero-based indexing, the third element is array of 2, and each element in the array is a word which is 2 bytes wide. So we put in si the value 4. You can see here that we use the multiplication symbol. The assembler is capable of calculating the result of constant expressions and putting the result in the resulting machine code. However, you can't write move bx ax times 2. Ax is not known at compile time, so it is not a constant. For that, you have to use the multiply instruction. Referencing memory is the only place where you can put registers in an expression. Finally, we put into AX the third element in the array by referencing the memory location at BX plus SI. BX is our base register and SI is our index register. Now back to our operating system. Okay. The code segment register has been set up for us by the BIOS and it points to segment 0. There are some BIOSes out there which actually jump to our code using a different segment and offset, such as segment 7C0, offset 0, so the standard behavior is to use segment 0, offset 7C0.
Стоп! У меня, я только сейчас заметил, у меня микрофон писец. У меня микрофон был вверх отпущен, то есть есть там, то есть у меня есть вот эта вот палка микрофонная, она, короче, у меня была вверх потянута, а не под ртом у меня стояла. Это Капец, меня еще не слышно было весь ролик, походу. Ну, наверное, не знаю.
0. We don't know if the data segment and extra segment are properly initialized, so this is what we have to do next. Since we can't write a constant directly to a segment register, we have to use an intermediary register. We will use AX. The move instruction copies the data from the source on the left side to the destination on the right side. We also set up the stack segment to 0 and the stack pointer to the beginning of our program. So what exactly is this stack? Basically,
Давайте я код спешу. Так. Теперь стек.
exactly is this?
Так.
Stack. Basically, the stack is a piece of memory that we can access in a first in, first out manner using the push and pop instructions. The stack also has a special purpose when using functions. When you call a function, the return address is added to the stack. When you return from a function, the processor will read the return address from the stack and then jump to it. Another thing to note about the stack is that it grows downwards. SP points to the top of the stack. When you push something, SP is decremented by the number of bytes pushed and then the data is written to memory. This is why we set up the stack to point to the start of our operating system, because it grows downwards.
Während Sie sich über Technik ärgern, die Ihre Erwartungen nicht erfüllt, sind wir für Sie da. Ja, genau. Hier unten. Da wir seit 30 Jahren den Nährroboter perfektionieren, wissen wir, wie man es richtig macht.
Ну круто, но почему мне никогда не высвечивается то, что надо пропустить можно? И еще одна реклама 20 секунд, это тоже нельзя пропустить. Ну что это за фигня, боже?
Trinkst du meine letzte Müllermilch?
Nee,
Was soll das denn?
ich befolge nur deine Regeln.
Die neue Müllermilch Typ Schoko-Kokos. Unwiderstehlich. Alles Müller?
Oder was?
If we set it up to the end of our program, it would overwrite our program. We don't want that, so we just put it somewhere where it won't overwrite anything. The beginning of our operating system is a pretty safe spot. Now we'll start coding a put_s function which prints a string to the screen. Always document your assembly functions. So our function will receive a pointer to a string EDSSI and it will print characters until it encounters a null character. Because I decided to write the function above me. Main, I have to add a jump instruction above, so main is still the entry point to our program. First, I push the registers that I'm going to modify to the stack, after which we enter the main loop. The load SB instruction loads a byte from the address ESSI into the AL register and then increments
Ну,
increments SI. Next, I wrote the loop exit condition. The OR instruction performs a bitwise OR and stores the result in the left-hand side operand, in this case AL. ORing a value to itself won't modify the value at all, but what it will modify is the flags register. If the result is 0, the 0 flag will be set. The next instruction is a conditional jump, which jumps to the done label if the 0 flag is set. So essentially, if the next character is null, we jump outside the loop. There's something I forgot when I recorded the video, a jump instruction to the loop label so that the code will loop. After exiting the loop, we pop the registers we previously pushed in reverse order, and then we return from this function. So far, our function takes a string, iterates every character until it encounters the null character, and then exits. What's left to do is to print the character to the screen. The way we can do that is
Он там
using
бился.
the by.
Пупакс, пупсай, What does B? What's next? Check the vinyl or all. Verify if next character is null. gz.done.
As the name suggests, the BIOS, or the basic input-output system, does more than just start the system. It also provides some very basic functions which allow us to do some very basic stuff, such as writing text to the screen. So how exactly do we call the BIOS to print a character for us? The answer is that we use interrupts. So what are interrupts? An interrupt is basically a signal which makes the processor stop whatever it is doing to handle that event. There are three possible ways of triggering an interrupt. The first way is through an exception. An exception is generated by the CPU if a critical
Да, я это слышал, я это знаю.
of the
Ну да.
Wait, let's add a string.
Так. Домашнее лицо. Луп. Не вижу, что там. И теперь MSG Hello. Мы сдаем ты Hello World 0. Новосай MSG Hello Call Put. И make Camo System RDA Build Main Floppy. Hello World. Hello World. И я, кстати, еще знаю один прикол. Прикольный. Он прикольный. Ой. Вроде VAX. Вроде VAX, да. Так. Ну, вода. Ну, еще прикол такой есть. Бум. Это не работает с таким видеорежимом. Ну ладно. Не очень-то и хотелось бы. Собственно, 30 минут. Ну, я думаю, то, что в целом можно ну что можно, думаю, посмотреть еще вот это видео. Это следующее по счету. И, конечно, опять те крамы, которые нельзя скипнуть.
Das neue Lenore Nordseebrise. Waschmittel, Weichspüler und Wäschewaffen.
Да вы что, угораете? Никакую рекламу нельзя скипнуть. Что за приколы?
Disk images directly.
Окей. Ну ты типа вообще на приколе, алло, YouTube. Я YouTube больше смотрю. И никакую скипнуть нельзя. Вот. Да мне посрать, иди нафиг.
Ultimativ sauber, ultimativ frisch. Spee, Qualität zum schlauen Preis. Außer Reichweite von Kindern aufbewahren.
Hello and welcome. This is part 2 of the Building an Operating System series. Today we'll learn how to load stuff from a floppy disk. Before talking about today's topic, I would like to correct some mistakes I made in the first episode. First of all, I said that the move instruction moves from the left to the right.
Блин, я забыл перевод. Перевести русский.
Which is incorrect. Move moves from right to left. You can think of it as an assignment in C. The destination is on the left side and the source is on the right side. Also in the referencing a memory location section, I said that when the segment is not specified, ES is used by default. This is mostly correct. However, as the viewer pointed out, when the base register is BP, SS will be the default. So far we've been limited to the first sector of a floppy disk, which is 512 bytes. This is very little space. We haven't reached the limit yet, but after today's episode we won't be far from it. So our number one priority is to implement some code which will load the rest of the operating system into memory. What this means is that we will have to split our operating system in two modules. The first one will load the second one. All operating systems are actually split this way because 512 bytes is not enough to fit even the most basic functions of an operating system. The first module is called a bootloader, and generally speaking it has several functions. It loads the most essential components of the operating system into memory, it puts the computer in the state that the kernel expects it to be in, and it collects some basic information about the system. Depending on the operating system, the bootloader can be very simple or very complex. Older operating systems like MS-DOS ran in 16-bit real mode, the mode we're using right now. So the bootloader's job was quite simple, to just load some binary and run it. More modern operating systems typically expect the bootloader to make the switch to 32-bit protected mode for and also collect some system information. We haven't talked a lot about 32-bit protected mode yet, but we will get there, I promise. However, one of its main limitations is that the BIOS functions that we talked about in part 1 can no longer be used. Some of these functions are really important as they provide us with critical information. For example, there is a function which shows us the memory layout, which parts of the memory are safe to use and which parts are reserved by hardware. Calling these functions is not possible once we are in 32-bit protected mode. So the responsibility falls upon the bootloader to collect all the required information before it starts the main kernel. A note here, by not possible, I mean possible, but we need to set up a lot of stuff until we get there, and we need that information a lot sooner than that, which is why I say it's not possible. Now that we know what we're going to be working on, let's talk a bit about floppy disks. Why in the world are we talking about floppy disks in 2021? That's a very good question. When getting started working on an operating system, a floppy disk is the simplest form of disk storage we can work with. It is universally supported by all BIOSes, as well as all virtualization software. Creating and working with disk images is very easy, and the FAT12 file system is rudimentary simple. All of these make it ideal for making operating systems, at least until we learn the basics and we can move to other storage devices. The simplest way in which we could use a disk would be to have the bootloader in the first sector or the boot sector, and the rest of the operating system starting from sector 2. This would be quite easy to implement. Our bootloader would read a number of sectors into memory and then start executing them. The problem with this approach is that we wouldn't be able to use the disk for storing any files, which is not very useful. We could design our own file system around that, but it's probably a better idea to use an existing standard one like FAT or EXT or NTFS, so that we can easily exchange data between our operating system and other operating systems like Windows and Linux. Let's get back to the code and continue from where we left off in part 1. This time
Yeah. Планку шорт открою. Тысяч. Вот это внимание не обращайте, да? Конечно. Так. Вот это. Что у меня тема поменялась, кстати, я не знаю, что это. Вон, посрать. Так. Атом Вандарк. Хорошо. Но было все время трава, но было просто совсем. Атом Вандарк. Нормально, нет? Атом Вандарк. Вот и петушня облигания. Пес. Я забыл, как эти настройки открывать нормально. Чем я занимаюсь? Как открывать фул настройки? Вот. Дима слепой. Так. Тема. Вандарк. Хорошо. Окей. Мы что-то тут выкрутили здесь, выкрутили.
Decided to use Visual Studio Code as the editor with the x86-64 assembly extension installed. Since we want to split our code into two modules, let's do that right now. I created two different directories in our source directory, one for the bootloader and one for the kernel. I put the same source file that we worked on in part 1 in both folders. Next we need to make some changes to our make file.
Was denn Zähne einzigartig macht, macht sie auch schwer zu reinigen. Ein abgenutzter Bürstenkopf macht die Reinigung noch schwieriger und hinterlässt Millionen Plaquebakterien. Ein neuer Oral-B-Bürstenkopf dagegen erreicht doch die Zahnzwischenräume und stellt so 100% Putzkraft wieder her. Also prüfen, wechseln und mit Oral-B dein perfektes Sauber zurückgewinnen.
Bauchschmerzen, Krämpfe. Buscopan bekämpft die Ursache, es löst den Krampf und lindert so die Schmerzen innerhalb von
both folders. Next, we need to make some changes to our makefile. To keep things organized, I declare some phony targets. This way we can keep our makefile cleaner by referring to various modules using their names rather than their output file names. Then I added a rule to tell make that the only floppy image target depends on the actual file, main floppy.img. In the floppy image dependencies, I replaced main.ping with the bootloader and the kernel targets. Next, I added the rules for building the bootloader. The always target will be used for creating the build directory if it doesn't exist, so we don't get caught.
Что за жесть?
Compilation errors if the directory doesn't exist. For the build rules, it's really simple.
Вау.
We just call NASM like we did before. For now, to build a boot.
Теперь ядро. Кирна, и там что-то типа.
Loader and the kernel, the steps are identical, so I just added the same rules for the kernel.
Так, сейчас списываем. Так.
Next, I created the always target, which simply creates the build directory if it doesn't exist. And the clean target will simply delete everything in the build folder.
Happy, happy, happy. Тун-тун-тун-тун-тун-тун. happy. Что это за баба-клаба? Где я это сохранял? Что за рофл? Что за рофл? Make plan. Make. Тысяч. Kernel. Все.
Let's give this a go and see what happens. Looks like we got an error when creating the floppy image. Ah yes, I forgot to change the file names in the main floppy.img rules. Talking about the floppy image, let's modify the way we create the image so that we actually create a FAT12 disk image.
Хорошо.
First, we need to generate an empty 1.44 megabyte file. We can do that using the dd command with the block size set to 512 and the block count set to 2880.
Да куда ты попёр? Хорошо. Дальше.
The next step is to create the files using the mkfs.fat command. The -f12 argument tells you to use fat12 and dash.
Ну как у меня называется? BOS. Butterfly OS.
N is used for the label, which.
Хорошо, давай.
Since we will overwrite it anyway. Next, we need to put the bootloader in the first sector of the disk. The simplest way to do that is to use the dd command with the conv equals no trunk option. It tells dd not to truncate the file, otherwise we will lose the rest of the image. Now that we have a file system, we can copy the files to the image.
No trunk.
One option could be to mount the image, but I don't really like doing that because we would have to run the image generation with elevated privileges. Fortunately, there's a collection of tools called mtools, which contains a bunch of utilities that we can use to manipulate FAT disk images directly without having to mount them. To copy the kernel.bin file to the disk, we can use the mcopy command.
Mcopy. Минус IBT ink Пинтир
Our makefile is now finished, so let's give it another go.
Хорошо.
Ultimativ gründlich. Egal ob 1, 3 oder 7 Tage Bart. Für eine spürbar glatte Haut und für eine Rasur wie am ersten Tag. Entdecke jetzt die Scherkopf-Wechselwochen mit 10 € Preisvorteil.
Ну, конечно, скипнуть нельзя, да, конечно.
Der unwiderstehliche Genuss aus Haselnusscreme, Milchcreme und Vollmilchschokolade. Schokofresh. Großer Genuss für kleine Momente.
And we're getting another error now. mcopy is complaining that the disk image is not valid. What happened? The issue here is that we have overwritten the first sector of the image with our bootloader. This section contains some important headers used by FAT12, so by overwriting them we have broken the file system. Can we fix this? Yes, we just need to add these headers to our bootloader. Going to the article about the FAT file system on the OS that...
Во, FAT, BBP, вот. BIOS параметр блок, вот это вот я слышал. Я вот читал код некоторых ОС, там тоже такая штука была, BBP называется, вот там. Это, короче, штука называется BIOS параметр блок, то есть получается, там находится хедер файловой системы, так сказать. Наверное, давайте source code. Чё с ютубом, аллей? Разгружу страницу. Так, 8 минут 18 секунд, сразу откатиться, наверное. Ладно, долго тут не откатилась. Так. Source code. Я даже знаю, где он будет находиться для интерпретации. Вот он, мне лень это все писать. Вот так вот. Скопируем. Вообще падлы жесткие нафиг. Просто на крысичах. Так, окей. И make. Хорошо, мы это сделали. Давайте это include low level with the butterfly OS build. Можно замонтировать и увидеть kernel bin. Батапим. 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 Так, ну я там.
This section contains some important values in the hex editor. You can figure. Let's begin. Let's be short.
Осуждаю, блин, брейнрутов. Короче, ладно, мне уже мозги поплыли. Я даже разговаривать разучился. Короче, капец. Давай. Опа. Блин. Ставь. Так. Butterfly OS. Вот.
By running the mdir command. Before beginning to implement our disk reading operation, it is useful to understand.
Поторпим. Inside Painful ink. Хорошо.
Understand how data is laid out on these disks. This applies to all format disks: floppies, CDs, DVDs, and hard drives. Looking at the round disk, if we divide it into rings, each ring represents a track or a cylinder. Another way of dividing the platter is into pizza slices. These are called sectors. Floppy disks, as well as hard disks, can store data on both sides of the platter, so we call each side a head. Hard disks can also have multiple platters, in which case we count each side of each platter as a head. To read or write something, we need a way to tell the disk controller where our data is. To read or write something, we need a way to tell the disk controller where our data is. So we can do that by giving it the cylinder number, the head number, and the sector number. This addressing scheme is called the cylinder head sector, or CHS scheme. While this scheme might make sense when you need to determine physically where the data is located on the disk, it is not very useful for us. When working with disks, We don't really care what data is physically located, we only care if it's at the beginning of the disk or the middle or the end. For that, we can use the logical
Так, 55 минут запись.
block addressing scheme, or LBA. Instead of a triplet of numbers, you only need one single number to reference a block on the disk. Unfortunately, the BIOS function we will use only supports CHS addressing, so we will have to make the conversion ourselves. Another thing I'd like to mention is that in most modern disks, the physical layout of the data has gotten a lot more complex, and the disk controllers only pretend to have cylinders, heads, and sectors to maintain compatibility with this legacy addressing scheme. But they have their own methods of determining the physical location of the data. In the CHS scheme, the cylinder and head are indexed from 0, but the sector starts from 1. Taking this into consideration, we can come up with the following formulas for making the conversion. We have two constants. The number of sectors per track, or the number of sectors per cylinder, meaning how many sectors we can fit in a single track on a single side of the platter, and the number of heads per cylinder, which is simply the number of faces the entire disk has. The sector is obtained by taking the remainder of the logical block address divided by the number of sectors per track and then adding 1. For the head, we perform the same division, and this time we take the result and divide it again by the number of heads per cylinder, from which we take the remainder. The cylinder is calculated by taking the result of the last division, that is, the logical block address divided by the number of sectors per track, and then divided by the number of heads per cylinder. Let's write this into assembly.
It should cost $1 billion to look this good. I'm too busy.
1 million and the new million gold elixir by Raban.
Kanaya, Regel Nummer 1. Wenn du was im Leben willst, musst du dir einfach nehmen. Trinkst du meine letzte Müllermilch?
Nee,
Was soll das denn?
ich befolge nur deine Regeln.
Die neue Müllermilch Typ Schokokokos. Unwiderstehlich. Alles Müller?
Oder was?
We will write a function which will take the LBA address in the AX register, and to make things easier for us, we will store the result exactly how the BIOS function expects us to. So the cylinder will be in CX in bits 6 to 15, the sector will be in CX bits 0 to 5, and the head number will be in the DH register. We can begin by dividing the logical block address stored in AX by the number of sectors per track. That number is a word, so we need to clear DX because the div instruction divides DX AX to the word operand.
Ладно, короче, я уже устал. Так-то час видос идет. Вам всем давайте удачи, пока я буду отдыхать.